I just finished doing this video on fractals, and after I was done, I came back and looked at it a couple days later and realized I'd made a mistake in the video. So because I put a lot of extra little clips in here, I don't want to redo it. So as you watch this video, look for the mistake, and when we get to the point where the mistake occurs, I'll come on again and point it out to you. In the previous video on sequences, we did a little construction for the Sierpinski triangle. I want to get back and just add a couple more things to that. But before I do that, I want to take you to the dictionary to show you that these fractals that we're talking about are not something that are real far out. The definition for them is right in the dictionary. Here we have the definition of a fractal from the dictionary. And if we look down here and read the definition, it says this: any of various extremely irregular curves or shapes for which any suitably chosen part is similar in shape to a given larger or smaller part when magnified or reduced to the same size. So that dictionary definition, what it's talking about is that property of self-similarity that all fractals have. And so let's go take a look at the Sierpinski triangle again and zoom in on it. Okay, so here's our Sierpinski triangle, and we're zooming in on it. And you can see it just keeps reappearing over and over again. Each complete piece of the Sierpinski triangle has all the information in the complete triangle. So again, that property of self-similarity, pretty interesting property. Now let's go back to the board here. This is what we did in the last video. We kind of derived or constructed the Sierpinski triangle, stage 0, stage 1, stage 2, stage 3. And then we said, okay, what if the area, the shaded area right there is 1? What is going to be the area of the shaded region here? And we decided that would be 3/4. For this stage right here, 3/4 of 3/4, so 3/4 times 3/4. Down here, 3/4 times 3/4 times 3/4. So what I want to do is take the stage numbers here and write them below these areas and see if we can't make some generalization about this. Stage 0, the area is 1. Stage 1, the area is 3/4. Stage 2, 3/4 times 3/4. Stage 3, 3/4 times 3/4 times 3/4. So I think you can see at stage 3, it's 3/4 to the third. At stage 2, 3/4 to the second. Stage 1, 3/4 to the 1, and at stage 0, 3/4 to the 0. So if I was to go out to the nth stage of the Sierpinski triangle, I could write a formula here for its area, and that would be 3/4 to the nth power. So then the question is, as n goes towards infinity right here, what is this going towards? Well, if you were a calculus student, you would write it down like this. You would say the limit as n goes to infinity of 3/4 to the n is, and with calculus and a little study of calculus, you know for a fact that this comes out to be 0. And so 3/4 to the n as n goes to infinity goes to 0, and that's why we say in the end result, when we go all the way out to infinity with the Sierpinski triangle, we have a geometric figure that has 0 area to it. Another way to look at it might be to just say, well, these points right here are points on the curve y equal 3/4 to the x power. If you had your little graphing calculator or whatever and wanted to graph y equal 3/4 to the x, that graph would look like this green curve right here. And although these are distinct points right here, this point is the point x equal 1, y equal 3/4, corresponds to that. This would be the point 2 and 9/16. This would be the point x equal 3, y equal 27 over 64. And so as you travel down here, what you see on this graph is this graph gets closer and closer to the x-axis, never touches it, never crosses it, but gets as close as you want to it. So we call this x-axis when this is happening an asymptote for that graph. And what it means is that that curve is getting as close as you want to 0. In other words, we're saying the area goes to 0 as n goes to infinity. Okay, do you see the mistake? It's not here in the part of the graph that we're working with. It's over here. The graph doesn't look like that on this side of the number 1. And you can see it when you look over here at stage 0, at x equals 0, the graph crosses the y-axis at y equal 1. So instead of the graph going up like this, when x is equal to 0, y should be equal to 1. And then as I go over here to -1, 3/4 to the -1 is 4/3, so that's going to be 1 1/3. And the graph, instead of going up like this right here, is going to come through those points and go up like this. So that's the mistake in the graph. It's not in the part that we talked about over here. Everything I said is exactly right. But over here, the graph, you can see I've just drawn it wrong right here. It should go through the y-axis at 1 and then continue on up like that. Okay, now back to the video. Okay, let's take a look and see what the Sierpinski triangle looks like in one more dimension, in 3 dimensions instead of just 2. This is what's called a Sierpinski pyramid. It's a 3-dimensional Sierpinski triangle, and you keep removing little pyramids from in the middle and then in the middle of each of those, so on and so forth. So you end up with a geometric figure, a 3-dimensional one, that has infinite surface area enclosing 0 volume. This is a postage stamp, and it has on it a little depiction of that Sierpinski pyramid. So there's a number of other postage stamps that also have fractals on them. Now I want to take you back to the Mandelbrot set, do one more little video so we can do a little zoom in on that, see what you think. Okay, here we have our Mandelbrot set, and what I want to do is start to zoom in on it. And as I zoom in, I'm going to see that another complete piece of the Mandelbrot set appears, so I'll press pause here. That's the Mandelbrot set. That contains all the information that you've just seen and all the information that you will see. Now let's continue to zoom in. As we zoom in, every now and then we'll see a complete piece of the Mandelbrot set go by. That has all the information in it that we've just seen and all the information in it that we will see. So there goes one right there. Okay, so let's just back up our recording, go back the other way to where we started. Now we're zooming back out. We see all the information pass on by, and we get a nice intuitive feel for that property of self-similarity that all fractals have. I always like watching that zoom in on the Mandelbrot set. Now we only have a couple more of these videos on sequences to do, but you might say the best is yet to come. Now if you haven't watched the first 6 of these videos, I suggest that you do so before we put up the next one. If you're a little pressed for time, you can't watch all 6 of them, then at least watch the one on Pascal's triangle. You'll be glad that you did. So keep tuning into YouTube, and we'll keep putting these videos up.